Hey guys, let's go over the quiz of the week. It's another thing I tried to put together that would sort of represent what's going to be in the quiz. The second question was selected by the College Board as being similar to what's going to be on the exam, and the first one is just one that hits similar things that they're looking for. So let's get to it. So first guy, it's a bit more traditional. We got first our situation. We got our mass hanging from a pulley, which is attached to a block. That block's connected to another pulley, which is connected to block A. There's no friction between B and the table. There is friction between A and B, and the thing's not moving. So let's take a look. First guy, or block A, we've got gravity down on it, mass of A times G. We've got tension 1, I called it because it's string 1, pulling back. We've got normal force of B on A. I'm just labeling things like that. And we got the force of friction between A and B. It is, the tension is trying to pull A to the left, so the force of friction is opposing that and pulling to the right. So that's the first guy. Second guy, a little trickier. We got tension 1 pulling it back, friction between B and A. If friction is pulling A to the right, the equal and opposite force is A is pulling B to the left. So both friction and T1 are both trying to pull it to the left. We also have the normal force of the table on B, this big guy here. We have a normal force of A on B down. That was equal and opposite to the force of gravity on block A. And we also have the force of gravity on block B. And tension 2 trying to pull it forward. And these guys cancel. I said this was equal, but apparently we're not supposed to know that for a second. All right, for the next bit, we're trying to derive the max value for mass C while they'll remain at rest. So if we made mass C any bigger, it would start to move. We're using static friction forces, so I'm not using any mu K's. I'm only using mu S, coefficient of static friction. First thing, looking at the horizontal forces on block A, we come to an important conclusion. Left and right forces got to cancel because it's not moving, so tension 1 is equal to the force of friction. By the way, this force of friction is the same as this force of friction. They're equal and opposite forces, Newton's third law. The force of friction of B on A is the same as the force of friction of A on B in opposite directions. So tension 1 is equal to the force of friction. Geez, I forgot the G. Mu S MAG. There we are. So it's equal to force of friction, which we can use here. Because if we look at the force of friction on the horizontal forces on B, we got friction to the left and tension 1 to the left, and they're equal and opposite to tension 2. These guys add up to equal tension 2, but we just said tension 1 is equal to the force of friction, so really we got 2 forces of friction here. So just 2 times that. These 2 are equal. And that's going to equal the force of gravity on block C. Since block C is not accelerating, all its force is going towards pulling this guy. And then we can just solve for our block C. We set this up. If these 2 are equal, that means that if we're at the maximum MC. If MC was too small, this formula for force of friction gives you the max force of friction possible, so it wouldn't actually be pulling at that. But if this is the maximum, then it would be equal. So the maximum MC we can do without it moving is 2 times the force of friction, which is coefficient of static friction, mass of A times G. Because this is equal and opposite to the normal force, the MAG. Of B on A. All right, so that's that guy. Then going along here, we're basically, we've got a given total mass here. We've basically gotten rid of A and we got a chunk of clay, which is some movable mass that can stick to either block. So we're going to have a total mass of 5 kilos, and we're just going to shift mass from B to C, and that's it. So we've got a changing MC, but a constant total mass for the system, and we're going to plot AC versus MC, and so we're supposed to draw a best fit line, and this is something halfway reasonable I did. This looks a bit like an outlier, so I might have wanted to arc it up a touch, but I didn't. Whatever. Use the best fit line for part C to calculate an experimental value for the acceleration G due to gravity. Your slope, like if you look at this formula right here, your acceleration equals mcg over m total. If we move this guy down, like our slope is AC divided by mc, it'll equal g over the total mass. So this is what I'm saying here. My slope is equal to g over the total mass. My slope is just rise over run. So we got 4.5 divided by 2.4 equals g over 5. It was said that the total mass is 5 kilograms. We can kick this guy up and we get 9.375. I think my line was a little too shallow because the official answer key says I should get around 10, but this is likely fine. It doesn't have to be exactly 10. No one's going to draw exactly the same line of best fit. All right, and then if the mass in the pulley is significant, so in that case it does have like a moment enough to affect the results, we're going to end up with, instead of, where's my mouse? There we are. So instead of having our formula like this, or G is equal to M total A over MC, it would secretly look like this. So G would actually be equal to A times M total I over R squared. So this would be, G should be bigger in this case, but if we're assuming we're using this formula, when we should be using this formula, we will calculate a value of G that is less than what it should be. So that's about it. If you've got a pulley, your acceleration is related to G, like you need to multiply it by a larger number because G is having to do more. It also has to accelerate the pulley as well as increase the mass, so a smaller acceleration corresponds to a larger G. So if you're still using this formula, you'll calculate it less than it should be. In this guy here, I went a little overboard after looking at the answer. They seem to be kind of like hand wavy. Anyway here, so to provide a straight line graph, or what do? We do the same thing here, but we're changing the total mass. So instead of moving the clay from block B to block C, we just put it aside. So we're changing the total mass of the system, but MC is staying constant, and we're measuring the acceleration. So we're saying, hey, what would provide a straight line graph that we could determine an experiment value for G? What two quantities should the students now graph? And if you want to do this, your slope should, if you want to calculate G, your slope should always equal some constant. It shouldn't be one of your variable things. Times G, it could be 1 divided that too. You could still solve for it that way. If it's sort of 1 over G, or like 1 over a constant times G, or constant divided by G, or constant times G. Anyway, if your slope is anything kind of like that, has no variable other quantities in it, it's reasonable to solve for. If this is our formula, we basically want to cancel out. So after we found the slope does not include AC or M total. These are the only two that do that. In this case, our slope is equal to G. If you think about this, if we do AC divided by MC divided by M total, that just equals G. So we just divide this junk from AC, we're left with G. So it's perfect. Find the slope, we're done. It's the acceleration of gravity. For this guy, if we did AC divided by 1 over M total, that would equal MC times G. If you just think, if you're dividing by M total, it's the same as multiplying by M total. So AC times M total is equal to MCG. All these other guys give you some other garbagey slope, which always includes either M total or AC. This one in particular is, if you do the math, it would end up being MCG divided by M total squared. Some of these other guys would solve for AC over G, like just not very useful. Anyway, the official solution seemed to be going for something much lighter. I believe it was just, if it ever loads. So here's your official answer. By removing the clay, the total mass is a variable. As the total mass of the system is decreased, the acceleration increased. Thus AC versus 1 over M total. Like, I feel this isn't as good an explanation, but apparently that's good for 2 marks. So there we are. All right, on to the next question. Sorry, this is going to be a longer video. But if we're going into this guy, the way they're intending to solve this guy, well, first of all, the question is, hey, you've got this cart. It's attached to a spring on a slope. It's got an angle that the slope has. The cart's big enough you can actually add stuff to it, and so that's kind of where they're leaning. And basically their idea is, can we do something kind of similar to the last question? Can we come up with a bunch of points and make a little graph and use the slope to solve for acceleration of gravity again? There's definitely going to be one of these stupid experimental design questions on the exam, but whatever. It's useful things to be able to do. They're intending, the idea is measuring the stretch in the spring while adding weights to this and just seeing how the stretch of the spring changes and then plotting all that. Anyway, first question, briefly identify each quantity to be measured, the symbols used to represent that quantity, and the equipment that would be used to measure the quantity. Things you need are, you need to know the mass of the cart, M, and if you're using additional masses, if that's your strategy, you need to also measure those, and you'd use like an electronic balance to measure that. You'd also need to measure the angle of the ramp incline. You can use a protractor, or if you've got a meter stick, you can measure the length of the ramp and the height of the highest point, and then just use trig. However you want to say it, protractor is probably easiest. Spring stretch from its equilibrium position. Apparently that's cool. You don't have to measure like the equilibrium position and then the total. So just how far it's stretched. You can just measure that with a meter stick. And potentially the additional masses. I was originally thinking of just varying the angle of the ramp. That way you don't need the additional masses, and you can do that, though it's a little funnier when you're finding the slope of the graph, but not too bad. You just plot things versus sine theta. Yeah, not terrible. Anyway, so you gotta describe your procedure used to determine the acceleration due to gravity, provide enough detail so another student could replicate the experiment, including any steps necessary to reduce experimental uncertainty. So basically you're gonna describe measuring everything you need above, like, hey, use the electronic balance to measure the mass of the cart, use the length to measure the stretch of the spring, use the protractor to find the angle, and then measure the stretch of the spring with no weights in the cart, and then measure it with different numbers of weights in the cart. It also, one thing it mentioned is including any steps necessary to reduce experimental uncertainty. That may be important. In the sample answer, it had repeat your measurements multiple times with the same mass to reduce uncertainty in their measurements. So just repeat your steps a couple of times just to double check you haven't screwed it up. Yeah, so apparently you should do that. And then which quantities which were measured in part B could be graphed on the horizontal and vertical axes to produce a graph that could be used to determine the acceleration due to gravity. In this case, you'd want to do something like stretch of the spring versus the total mass of the cart plus masses. Something like that would work great. Yeah. And then describe what information from the graph, describe part C would be used and how it would be used to determine the acceleration due to gravity. If you did this whole like add masses to the cart method and you did spring stretch versus the total mass. In this case, you'd have the situation where it's kind of like your like F parallel would be equal and opposite to your spring force. So you'd have K delta X equals mg sine theta. So if you did delta X over m, that would equal as your slope. If this is your slope, then it would be g sine theta all over k is equal to your slope. So you'd find your slope, you'd plot it, it would be equal to g sine theta, and so after you're done, you would divide out sine theta over k, and you'd end up with your acceleration of gravity. And then the last step uses oscillations, which we've covered, but will not be on the final. This is actually fairly easy if you remember your formulas. It says, how could we figure out the mass if we had this thing? This is very much a period question. So you've got the cart oscillating back and forth, and it's pretty easy to find the period. That's just the time to do its thing once. If you look at your crest to crest distance, it looks like it's about 1 second. Your period formula from that unit is 2 pi root m over k. If you know k and you know your period, which is 1 second, you can totally solve for m. So just say something like that and you're done. Sorry to be pushing 20 minutes here, but hopefully that helps. Have a good one.